Okay, honors chemistry people, today we are going to talk about radioactive decay and how it goes into half-lives. Okay, so especially when we have really large elements, even if we don't have super large elements, if we have elements that are really far away from that band of stability in terms of their isotope, it usually takes them a couple different decay series to decay to an element that is stable. So when we talk about radioactive decay series, we're talking about a series of reactions that an element will go under in order to finally arrive at a stable isotope. So we begin with unstable nuclei and result in the stable nucleus. Here's the decay series for uranium-238. Now, as I said in the previous video, lead-207 is our last stable isotope. So it's going to take a long time to go from uranium all the way down to lead. First, uranium decays to thorium-234, which then in turn decays to protactinium-234. Decay reactions continue until a stable nucleus, lead-206, is formed. So here we go. Notice we have a chart here that gives us the type of decay and the element. So we have our mass number down here on our x-axis, and on our y-axis we have our atomic number. Okay, it's usually done the opposite way, but this graph does it this way. We have the types of decay indicated by red arrows going to the left are alpha decay, and beta arrows going up are beta decay. So we have a uranium-238 right here, alpha decay to thorium, and then we have thorium beta to protactinium back to uranium. But now we're at uranium-234, different isotope. Then we do alpha again to thorium, alpha to radium, radon, polonium, then lead-214. But lead-214 is not stable. We have to get all the way down to lead-206. So we do a beta to bismuth and a beta back to polonium. Once again, different isotope. Alpha back to lead, different isotope here. Beta back to bismuth, different isotope from this bismuth. And polonium, once again, different isotope. And then finally, an alpha to a stable isotope of lead. Notice we had many, many iterations. Now, all of these decays happen at different speeds. I want to go over some of those speeds. Some of these speeds on these decays are really quick, and some of these decays are really slow. So let's go over some of the timing that happens in these decays. Now, this first alpha decay from uranium to thorium, uranium-238 to thorium, the half-life of this is 4.5 times 10 to the 9th years, or 4.5 billion years. So that's an extremely long decay process, okay? But when we go from this thorium to this protactinium, this half-life here is 24 days. So my question is, why do we have different half-lives? Why do some of these go super fast and some of these go super slow? I want you to think about this. We're going to talk about some more time. This half-life is 1.2 minutes. It's super fast. This one is, this one is 2.5 times 10 to the 5th years. Okay, that's not what I wanted to do. This is 2.5 times 10 to the 5th years. This is 8 times 10 to the 4th years. And this is 1,600 years. And this one here is 3.8 days. Okay. This one's 3 minutes. This one's 20 minutes. This one right here is 27 minutes. This one right here is 160 microseconds, super fast. This one is 21 years. This one right here is 5 days. And then the last one, the half-life here, is 138 days. So notice we have half-lives that go from the billions of years, super long, way longer than, even some of the major Earth cycles on the Earth. And then we have half-lives that are super small, that are just microseconds. Why the difference? Why do you think we have such a difference? Now, if you compared how far these different isotopes were from that band of stability compared to how long long or short their half-lives were, you would see that the further those isotopes are from that black line of that band of stability where we have stable nucleons, the further they are out, the faster the half-life is. The closer they get to that black line where we have the stable nucleons, the longer the half-life is. So the more we get to that stable line, the more it takes for those nucleons to decay. So that's a really good indicator. And there are a couple graphs. I haven't been able to find a really good graph on half-life time versus distance to the nucleon, to the stable nucleon. But the more you are away from the stable, the faster the half-life is. Okay, so we're going to talk about radioactive dating and half-life and what a half-life means. So this is a definition that you should have. Half-life is the time that is required for 1/2 of the radioisotope's nuclei to decay into its product. So for example, if I had 100 grams of something and I went through one half-life, and we do lambda for the symbol of half-life. So that means half-life. I would have 50 grams after one half-life. If I allowed it to go through another half-life circle, what's half of 50? I would have 25 grams. And then if I went through another half-life, I would have 12.5 grams. And I went through another half-life, I would have 6.25 grams, and so on. So technically, would I ever technically get to zero? No, because this is what we call an exponential factor. We are going to go like this. Eventually, we will physically get to the last atom decaying, but mathematically, we never technically get to zero. Okay? So, half-life is an exponential thing. So here's a couple of examples. The decay of strontium-90. Now, the half-life of strontium-90 is 29 years. So if I started with 10 grams and went to 29 years, I would have 5 grams left. If I went 58 years, I would do half-life twice, and I would have 2.5 grams. And if I did 3 half-lives, I would have 1/2 to the third power, right? Would this be the same as 1/2 to the third power? So I would divide it by 8, so I would have 1.25 grams. And if I had 4 half-lives, I would have 1/2 to the fourth power. So I would be dividing by 16, right? And I would have 0.625. We will notice that we have this exponential decay pattern going on. Okay. Now, as I said in the radioactive series, we have very different half-lives depending on the different isotope we are dealing with. So here's another couple of examples. Polonium-214. Here's a symbol for polonium-214. Notice the mass numbers on the bottom and the proton number is on, or the mass numbers on the top and the proton numbers on the bottom. We have a half-life of 163.7 microseconds. So that's a super, super short half-life. It's so short that, in fact, it's almost impossible to get polonium-214. Cobalt-60 has a half-life of 5.272 years. Now, if you've ever known anyone who has gone under radiation therapy for breast cancer, they use cobalt-60 a lot for that. Radon-222 has a half-life of 3.8 days. We actually have a lot of radon here in Utah because we have uranium up in the hills, in those granite hills up in the East Bench. And part of the uranium decay process is radon. And so if you've ever heard of radon poisoning, it's a gas that is super radioactive. It has a super short half-life. Hopefully you've had your house tested for radon because it causes a lot of lung cancer. Okay. Phosphorus-32 has a half-life of 14.28 days. We use a lot of phosphorus-32 for biological tracers when we're trying to get biological metabolisms and pathways organized in the lab to see what's going on. So we will trace where the phosphorus-32 is going. Carbon-14 has a half-life of 5,730 years. We use that for anthropological dating. And uranium-238 has a half-life of 4.46 times 10 to the ninth, or 4.46 billion years. Okay? So let's talk a little bit about carbon dating here. Carbon dating makes use of the radioactive decay of carbon-14, which is formed by cosmic rays up in the upper atmosphere, up in the stratosphere. So it's above the ozone level, where the UV rays are not really filtered out by the ozone. And the UV rays go and they hit nitrogen, and they knock one of the protons in the nitrogen out, and the UV rays create a neutron, which makes it carbon-14. And this happens at a very constant rate. Therefore, the carbon-14 atoms become very evenly spread throughout the Earth's biosphere. So everything that's living is constantly taking up carbon. Because most of the food that we eat, we are carbon-based life forms. Plants are carbon-based life forms. We're carbon-based life forms. Almost everything that we eat, and I'm going to grab out snacks, most of this is carbon. My cashews that I have in here. Okay? So every time I'm eating more carbon-14 because the carbon-14 that made those cashews is absorbed from the atmosphere when the cashew tree created those cashews. Okay? Plants use that carbon dioxide in the atmosphere from the environment, which contains all of those isotopes in that constant ratio, okay, to build the more complex molecules that we all eat. Okay? When animals eat plants, and the plants absorb the carbon-14 that were part of the plant, they all become part of us. We are all carrying around carbon-14 atoms right now, carbon-12 and carbon-13. Okay? So yes, you are radioactive. I'm radioactive. We all are. Okay? However, when we die, when any plant or animal dies, that means we aren't eating things anymore. That means we aren't taking in more carbon-14. Therefore, our ratio of carbon-14 to carbon-12 and carbon-13 starts to change from the atmosphere because the carbon-14 that makes us up starts to decay. Okay? So that carbon-14 starts to undergo beta decay and turn into nitrogen-14. So what we can do is we can compare the carbon-14 ratio in the atmosphere compared to the carbon-14 in the old artifact or the remains of whatever humanoid or animal that we found. And then once we compare the ratios, we can get a pretty good idea of how old that artifact is, or that humanoid or that animal is. And we can date it, usually within a precision of about 200 years, which is pretty good. Okay, so the half-life of carbon-14 is 5,730 years. Because the amount of stable carbon in a dead organism remains constant while carbon-14 continues to decay, we use that ratio. Okay? So carbon-14, the half-life, I would also use the symbol lambda, is 5,730 years. How old is an artifact if 25% is remaining? So let's look at this. Let's pretend if I have 100%. Now, if I undergo one half-life, I will have 50%. I'm not quite to 25 yet. So if I undergo another half-life, half of 50% is 25%. So I've got the 25% that I'm looking for. So now I need to look and count how many half-lives I've undergone. I've undergone 2 half-lives. So what would be the way to figure this out is to take the half-life time and multiply it by 2. So I have undergone 2 half-lives, and every half-life is 5,730 years. So when I multiply that out, I get 11,460 years. Now, do I know that that artifact is exactly 11,460 years? No, I don't know that it's exactly that. But I can say it's that plus or minus about 200 years. So that gives me a ballpark of how old that artifact was. Okay? So let's do another example here. How much of a 10-gram sample of americium-241 remains after 4 half-lives? Americium-241 is a radioisotope commonly used in smoke detectors and has a half-life of 430 years. So yes, you have americium-241 in your house. If you have a smoke detector, they are using americium-241 to do that. Okay, so let's look at this. We can do this the long way. We can just take 10 and keep dividing it 4 times. So if I undergo 1 half-life, I will have 5 grams. I undergo 2 half-lives, I will have 2.5 grams. If I undergo yet another 3rd half-life, I will have 1.25 grams. And here's my 4th half-life, I will have 0.625 grams. Okay, that's the long way to get to it. Now, the other way I could do this is do this. I could take my original mass and I could multiply it by 1/2. And I said I wanted to do 4 half-lives. So I'm going to raise that 1/2 to my number of half-lives. Okay? So 1/2 to the 4th times 10 will also give us 0.625 grams of americium-241. Okay? This is probably the easier way to do it. All right? So I want to just write an equation off to the side here. N naught multiplied by 1/2 to the n, where n is the number of half-lives, n naught is your original mass, is equal to capital N, this is what is remaining. Notice I set this up that way, right? I have my original mass here. I have 1/2 raised to the number of half-lives, and it gives me what is remaining. Okay, so that's the equation that I used. So if the passing of, let's go on to the next one. If the passing of 5 half-lives leaves 0.25 milligrams of strontium of a sample, strontium-90 sample, how much was present in the beginning? Now, we can do this the long way. We can go back 5 half-lives, and I'll show you that. So if I start at 25 milligrams and I reverse my half-lives, I would have 50 milligrams. That's 1 half-life. 2 half-lives, 100 milligrams. 3 half-lives, I would have 200 milligrams. Let's see, that's 3. 4 half-lives, I would have 400 milligrams. And 5 half-lives, I would have 800 milligrams. Okay, that's writing it out the long way. 1, 2, 3, 4, 5 half-lives. I can use this equation that I just gave you up top as well. So I have 25 milligrams, and that is equal to my original stuff multiplied by 1/2 to the 5th power, because I did 5 half-lives, right? So 1/2 to the 5th power, if I do that, is equal to, let's see, I will get 25.0 is equal to 0.03125 multiplied by n naught. So what I need to now do is take that 0.3215 and divide, take that and divide 25 by it. So let's do that. 25 divided by 0.03125 gives me 800 for my n naught. So we can do it both ways. I personally like using the equation instead of writing it backwards like that, but whatever way you're comfortable doing, okay? All right, number 10. Let's see if I can get this to scroll. Is this going to scroll for me? Yeah, it's thinking. The table below shows the amount of radioisotopes in 3 different samples. To the nearest gram, how much will be in sample B when sample C, oh my, what just happened? When sample C has 16.2 remaining. Okay, so if I look at this, 16.2, we are going to use this equation right here. Okay. N is equal to n naught multiplied by 1/2 raised to the t divided by half-life. So lambda here is the half-life time. T is the time that is happening, okay? Now, in order to do this, we have to be able to figure out the time that's going to happen. So we want to look and see when sample A has 16.2 remaining. So let's figure out, let's divide 64.8 divided by 16.2. Hopefully you get 4, right? So that means that we have 1/4 of what's going on. So that means we've done 2 half-lives right here, right? So our half-life here is 5.27 years. So 2 of those, 5.27 years times 2, will give me a time of 10.54. Okay? So what I can do, I have my half-life of B right here, and I want to know how much time or how much will be left. So when I look at B, and I'm only going to do it for B. So my N naught for B is 58.4 grams multiplied by 1/2. And the time that we're doing is 10.4. And our half-life here is 12.32. So you're going to need to use your caret key on your calculator. Here, I don't know if you know your caret key, but this caret key is going to be your friend right here. So this is how I would put it in. So I'm going to focus on my calculator right here. I'm going to put this in as 58.4, and I'm going to raise this caret key. Actually, no, sorry, 58.4 times 0.5, and I'm going to raise that 0.5 to 10.54. Oh my gosh, I haven't done this for so long. 58.4 multiplied by 0.5 caret key parentheses, because I need to do order operations. 10.54 divided by 12.32. That is how I would set that up in my calculator. Okay, so you need your exponent to be parentheses. So that would give me 32.27. Let's see, I have 3 sig figs, so 32.3 grams would be left. So I would have 32.3 grams of tritium left. Okay, that's enough of that. Let's go to some more. Example 11, krypton 85 is used as an indicator in lights of appliances. The half-life of krypton 85 is 11 years. How much of a 2 milligram sample remains after 33 years? Okay, so using that same formula that we used up above, N is equal to N naught multiplied by 1/2 raised to the T over lambda. Okay, so let's label what we've got here. We have N naught right here. We have lambda right here, and we have T right here. Okay, so we're going to plug those in. So we're going to take 2 milligrams. We're going to multiply it by 1/2 raised to the 33 over 11. Now, those of you who are sharp-eyed are going to realize that this 33 over 11 reduces to 3. So you could also just put it in there as a 3. So 2 multiplied by 0.5 raised to the 3, we are going to have, oops, I don't want that color anymore. We are going to have 0.25 0. Let's see, we have 4 sig figs, 1, 2, 3, 4 milligrams of krypton 85 left after 33 years. Okay? Just for fun, here's another example. The Shroud of Turin. It was a shroud that they had in the monastery in Torino or Turin, Italy, up in the Italian Alps. It's purported to have been the burial cloth of Jesus Christ. If so, it would have had to be approximately 2,000 years old. Researchers from 3 separate labs have completed radiocarbon dating on pieces of cloth. Find their results. So if you look at their results, you'll find that their results have this Shroud of Turin being about 800 to 1,000 years old. So that means that the Shroud of Turin actually originated the same time as the Crusades, when relics and things like that were really, really important. So they think that this was a manufactured relic as part of the Crusades. Okay, we get some nuclear reactions now. Actually, I think we're going to stop here. I'm going to talk about fusion and fission and what we look at those for a little bit longer in another video. So we'll talk to you later. Bye.